Hello, welcome back. In my previous video, we discussed how the integral test works. In this video, we're going to continue our discussion on what the integral test is and why we use it. So take a look at the following series. We have as n goes to infinity, 1 over 3 n plus 4. We know that it's very important to know whether or not this series converges or diverges. So let's expand the series. If we let n be 1, we get 1 over 7. Let n be 2, we get 1 over 10. If we let n be 3, we get 1 over 13. And if we let n be 4, we get 1 over 16. Now notice, the terms in the series are decreasing as their magnitude as n increases. In other words, what this is saying is that the limit is approaching zero. And that's what we said in my previous video. If a series is to converge, the series must approach zero. The values of that sequence must approach zero. And however, this does not guarantee that an integral that a series will converge. We talked about this when we covered improper integrals. Just because values get smaller doesn't mean that will converge. And we saw that with 1 over x. Remember, if we took the integral 1 over x dx from, let's say, 1 to infinity, this grew all the way to infinity. It approached infinity there. And so not just because the values tend to get smaller as the numbers get larger, as n gets large, it means it's going to converge all the time. So we got to be really careful with that. And that's what this test we're talking about does for us today. So all series, we just want to know if they converge or diverge. So to do this, and you saw in my previous video, we had something very similar to this. We look at the area under a curve. We're just going to look at the area. And what we have here is a function that a Riemann sum here. And if you notice, the values here are decreasing. They're getting smaller and smaller and smaller. And what we're going to do is we're going to use Riemann sums to find the area of that series. Because if that area converges, then we know the series has to converge. And that's kind of rule. So we're always looking at area. So Riemann sum is the area of a rectangle. And all this says right here is that, look, each rectangle has a width of 1 right here, and they have a height of a sub n. A sub 1, a sub 2, a sub 3, and so forth. So the area of each rectangle is just the height of that sequence at a sub n times 1, and we can reduce it to just a sub n. And that's really how we get our series equation right here. That if we let n go from 1 to infinity, we get our first term plus our second term plus our third term. However, as we talked in my previous video, we cannot add an infinite number of rectangles. So instead, we're going to use an integral to find if the series converges or diverges. So we're going to use an integral just to tell us if it converges or diverges. So we know from our last unit that if an integral, that we can use improper integrals um, to find out what happens as the number of terms go to infinity. So note, again, these are going to be improper. In other words, if we want to find our series, we're going to say that our series approximates this improper integral right here. Now, because it's improper, remember, we have a no-no up there. We can't let our bounds go to infinity. So we're going to use limits instead. Let b go to infinity instead. Now, here's a drawback. Now, the integral test, there has to be something happen, and we talked about this in the previous video. We need to guarantee that there's 3 guarantees that we have to have before we can apply this. Like 1, here's the 3 rules. 1, the function must be continuous. So that's step 1. We must say that we're going to pick a function and it has to be continuous. Two, always has to be positive values. But what if it's negative? Factor it out. Like if I have like a negative right here, a sub n, I can just write that as negative a sub n. I know. So it has to be always positive value. Really, what this is for, if we have an issue later on, which we're going to talk about alternating series. And the big one, decreasing. Now, what does it mean to be decreasing? It means as n goes to infinity, the values get smaller. F of x decreases. Now, be careful. Most of the time, we're going to deal with functions that look like rational functions. However, we could also have functions that bubble up a little bit, like so. This bubble right here doesn't affect it because this is still decreasing. So you can have little bubbles and that'll be okay right here. So here's what the integral test says. It says once you show that a function is continuous, positive, and decreasing, then we can consider the following. And here's what it says. We can use, that's all this says right here, we can use the integral to find the series. And here's what it says. If either diverges, so does the other. In other words, if the integral diverges, so does the series. If the integral converges, so does the series. We sometimes will say that the integral and the series go hand in hand. Hand in hand. So, sorry, let me there we go. That's terrible. So let's look at an example. Ready? Let's take a look here. Here we have our series from above. We want to find out if this will converge or diverge. And let's see here. We have 1 over 3n plus 4. So I'm just going to really quickly take the limit, let n go to infinity of this. And we should know this one right away. The bottom grows way faster than the top. So we know that that's going to be approaching 0. So it's decreasing. It does have a domain restriction, but it's at negative 4/3. So we don't worry about that. These will pretty much always be continuous. So what we're going to say is we are going to let f of x. So I want to find out if this series converges or diverges. So what I'm going to do is I'm going to convert it to a function, and I'm going to say let f of x be the following function, 1 over 3x plus 4. And this is continuous, got to spell it out, positive, there's no negatives there, and we just showed it's decreasing. Therefore, now we're going to take the integral from 1 to infinity, 1 over 3x plus 4 dx. Now, this is improper, so we're going to write it as a limit as b goes to forever, 1 over 3x plus 4 from 1 to b. This is a, oops, so forget my dx. This is a use substitution. We should be pretty good at these by now. This becomes now the limit as b goes to infinity. This now becomes 1/3 natural log 3x plus 4, and that goes from 1 to b. Applying the fundamental theorem, we get now the limit as b goes to infinity of 1/3 the natural log. Plug in the b, we get 3b plus 4 minus 1/3 the natural log. Plug in the 1, and I get 7. Now, if we let b go to infinity, what happens? Well, natural log of infinity is just infinity, so this is infinity. So therefore, this integral diverges. Well, what does it mean for our series? Well, remember, we're looking at area right here. So what it's saying is that the area here grows forever. So if my integral is going to go forever, and we know because of Riemann sums that that those rectangles will be less than my area underneath my rectangle, this will also that the series must also diverge. So therefore we say that the series, and we got to name the name, the series diverges by what we call the integral test. Spell it out. By the integral test. There it is. So let's try another one. 1 over n cubed. Again, if I take the limit, and I can do that in my head, the limit as n goes to forever, 1 over n cubed. This is going to be 0, so check. It's getting small, it's decreasing. So we're going to say let f of x equal 1 over x cubed. This is continuous, positive, and decreasing. We just showed us decreasing. Therefore, we're going to say our new integral, ready, from 1 to infinity of, and I'm just going to write this as x to the negative 1/3 there to help me with the antiderivative right here. And if we integrate, whoop, be careful, it is improper, so we got to rewrite it. The limit as b goes to forever. And I'm going to go ahead and integrate this. Why not? You know what I mean? I can go ahead and integrate this. This becomes negative 1 over 2x squared when you integrate that from 1 to b. Using our FTC, we're going to get the following, negative 1 over 2b squared. Plug in the 1, we get plus 1 over 2. Letting b go to forever, well, I'm going to wind up with infinity on bottom, so the whole first term is 0, and I get 1/2. Now, this is finite. Whoop. This is finite. Therefore, what does it mean? The integral converges. Now, be very careful. This doesn't mean the series equals 1/2. This is the integral. The integral equals 1/2, not the series. Because remember, when we looked at the area underneath here, when we looked at the area, the integral, the series is those rectangles. They're not the same as the area of the integral, which is the function itself. They're not the same. But we're just saying that, hey, because the integral is converging, and if the integral stops, we're saying that the series also must stop. So we're going to say, therefore, whoops, sorry, wrong color. Therefore, we will say that the series, we're going to say it, converges by the integral test. Now, you're going to want to say it converges to 1/2. Please avoid that evil temptation. All right, so thank you for this video. Go to my next one, and we're going to take a look at something. Whoops, I want to mention this real quick. Again, it's very important. We are not saying that the series equals the integral. In most cases, we'll never know what the value of the series will equal. We just know it converges. For example, pi, we can get pi from a series, 3.14159, and so forth. We know pi actually converges, but we don't know what it converges to. All right. So I will see you guys in the next video. Take care.